The next topic that is being discussed today is about genetic programming. Actually, genetic programming is a way of creating new programs or creating new algorithms. Actually, it is not creating new algorithms itself. It is actually finding out new ways of expressing the fitness functions or the way of solving problems, the newer ways of solving problems using the genetic algorithm procedure. That is, we are applying the genetic algorithm procedure or the concepts of genetic algorithm into program development. This is useful in the case of artificial intelligence as well as machine learning, where new programs are to be developed by the computer on its own. So let's see what is genetic programming and a short overview of how it can be implemented in computers. So genetic programming, or it is also known as GP. GP is for genetic programming. Is an evolutionary algorithm-based methodology inspired by the biological evolution to find computer programs that perform a user-defined tasks. So this is based on the evolutionary algorithm concept itself that we have discussed in our first module. So based on that concept, based on the biological evolution concepts, computer programs are developed, and these computer programs are developed in order to perform some user-defined tasks or some specific problem-solving operations that is to be done. So actually, this is a specialization of genetic algorithms. Actually, a special variant of genetic algorithm where the individuals in this case are the computer programs. Unlike in our genetic algorithm, in our normal genetic algorithm, what we does is the individuals are possible solutions of the given problem. But in the case of genetic programming, it is a special case of genetic algorithm where the individuals or the chromosomes that is being considered are possible computer programs. So it is the GP, the genetic programming actually automatically solves problems without requiring the user to know or specify the form of or the structure of the solution. So that's it. So the computer generates programs on its own, or finds out the best performing computer program on its own, and thus it solves the problem at hand also. So the user will not be knowing how to specify the structure of the solution, but the computer will be finding out it on its own. So that's the concept. Now the representation, how the codes, the program components are expressed in this genetic programming. That is an important part. Whenever we are thinking about genetic algorithm, the main thing that comes into our mind is how this problem can be expressed, or how this particular solution can be expressed in genetic algorithm, what data structure we should use. In the case of genetic programming also, the same question is there. The question is there in the case of genetic programming, it is very much relevant because we know that the individuals are computer programs. Then how we will represent computer programs into strings or into non-data types in the non-data types which can be expressed in order to do the crossover, the mutation, selection, reproduction, etc. Those type of procedures. That is the important thing. So how this is being represented, the programs are being represented is it is expressed as syntax trees rather than lines of code. So the lines of codes are converted into syntax trees. So how it is being converted, let's see. So then the variables, constants, etc. are the leaves of the trees, which are called the terminals, while the arithmetic operations are at the roots of or at the joints of these leaves, at the joints of these leaves, and these are called functions. So the root node acts as the glue. That is the leaves or the of the trees. The leaves of the trees represents the variables as well as the constants, and the roots, root nodes acts as the operations or the functions. So they act as the glue between the two or the different operators. I mean the different variables and constants. So this is a tree-based representation. So one tree-based representation is given here. Let's see it. So an expression is given on the right side, that is 2 pi plus x plus 3 minus y. So this is the expression 2y plus x plus 3 minus y divided by 5 plus 1. So this is the expression that is given, and we have to represent this particular expression. This is a part of a programming code. So this particular expression is represented as a tree here, as a tree representation. Being computer science students, you might be knowing what is a tree representation. So in this case, 2 times pi, so 2 into pi. So here these are the leaves, these are the leaf nodes. So in the leaf nodes, the constants as well as the expressions are represented, or the variables are represented. So 2 and pi. Then here is the operation or the function. Then again, this leaves two leaves. So in between these two, there is the plus symbol. Then the other one, 5 plus 1. So it is here. Then in between the symbol. So here is the other leaf node. So it is represented with y divided by 5 plus 1. So y divided by 5 plus 1. So that is it. And then this term x plus 3 minus y. So this is x plus 3, then minus this particular term. This was evaluated as y divided by 5 plus 1. So that is it. So then these two terms are to be added. So here is it. Then these two terms are to be added. So this is one term, that is 2 into pi, and this is the other term, x plus 3 minus y divided by 5 plus 1. So that is added together. So this is the tree-based representation method for expressions. The expressions are represented like this. Now some logical expressions. Logical expressions are represented like this, almost the same way. So here the x true, then x, y, z, x, and y. So these are at the leaf nodes. At the leaf nodes, they are there. So here x, true, x, y, z, then again x and y are there. So then the operations or the functions. This is the function. Here is the one. Here is one. Then here this one. This. All these expressions. These are the logical expressions used in computer science. So this type of, or mathematics also. In mathematics also we often see this type of representations. So these representations are done like this. That is, the leaf nodes constitutes the variables or the constants, and the root nodes represent the operations or the functions. So that's it. Then another tree-based representation of a programming code, that is I equal to 1 while I is less than 20, I equal to I plus 1. So this is some type of a C programming code or C++ type code. So in this case, how this is being implemented, I 1. So I equal to 1. So that is the initialization. So I equal to 1 is initialized here. Then here it is the semicolon. So this is the semicolon. So that is here. Then the next one, while is here. So this is I less than 20. I less than 20. So in that is while I less than 20. That is how it is being represented. While I less than 20, I equal to I plus 1. So this is how it is being represented. So this is the tree-based representation in case of genetic programming. That is how the programming codes can be represented in the form of a tree, that in the form of a syntax tree actually. So the thing that the expressions can be, the mathematical expressions can be converted into tree-based representation. The logical expressions can be converted into tree-based representation, as well as the programming codes or program snippets can be converted into tree-based representations. Then the genetic operators that are being used in genetic programming, these are the same as our genetic algorithm itself. There is no changes, but how it is being implemented in genetic programming, that is what we are seeing here. So the main operators used in genetic programming are reproduction, crossover, mutation. Obviously, selection is also there. Selection depends on the fitness value, the fitness, how it is being attributed to this a particular program. That is actually debatable, because any program, whether it gives the good result or not, that will be the fitness value that is assigned to it. So that's actually debatable, how the selection procedure is required or not, or how it is being selected or not, how the fitness value is being done. So based on what the literature says is that based on a single problem or a single problem, it can be fed into this particular genetic programming, so that the genetic programming operators or the genetic programming can find out a fitness value based on the solution quality of that particular program or that particular problem. It can be the solution quality, or it can be the time taken to obtain that particular solution, etc., etc. That can be, there are different modes of, or different criteria for finding out the solution quality, I mean the fitness function. So the main operators, as we said, the main operators used in genetic programming are reproduction, crossover, and mutation. So the reproduction is actually only just copying a selected individual to the next population. This is not being much used in the case of genetic algorithms, but in genetic algorithm also this can be used. The most fit individual can be directly copied to the next generation, no problem. So that is also possible, but mostly we are avoiding that type of reproduction conditions in the case of genetic algorithms. So in the case of this genetic programming, this is happening, that is in a generation, if there is a particular individual is there, that is this particular individual that is being copied to the next generation. So in the generation 1, this individual is there. So in the generation 2 also, the same individual is copied. So that is the reproduction procedure. And in the case of crossover operator, you know that is how it is being done. That is, two different parents will be there, and we will be having a crossover point, and with that crossover point, we split the parent into two separate parts, and then one part of the first parent is merged with the second part of the second parent, etc., etc. So that is the way. So in this case, say this is a parent, and here is the crossover point. This is the crossover point in this parent. This is the second parent. So this is another representation, some mathematical representation of mathematical function. So some mathematical expression actually is represented here in the form of a tree. So then here, this is in the second case, this is the crossover point. So then what happens is, it is replaced. So this part, this C, 2 into pi remains there. So x plus 3 plus minus. So this part, this entire part remains the same. See here, this entire part remains the same. So then what is replaced is this part. This part is replaced with what is happening in this part. So this part is replaced with this part. So that is y divided by 5 plus 1. Y divided by 5 plus 1 is replaced with a into 3. So here it is a into 3. So that is replaced. So how that, this is how this crossover operator is being done in the case of genetic programming. Here, see here what is happening. So this is the thing that is to be replaced here. That is a into 3 is to be replaced with y divided by 5 plus 1. So that is replaced here. So this is how the crossover operator is done in the case of genetic programming. So let's see another example of crossover. So see, this is a very simple expression, x divided by y plus 3. This is x divided by y plus 3. and this is y to the power y squared. So y to the power 2, y caret 2. So it is y squared minus x. So these are the two parents, x plus x divided by y plus 3 and y squared minus x. So the crossover point is this is here, and here it is here. So then the resulting one is one of the offspring, only one offspring is given, x divided by y squared. So this is resulting offspring, one of the offspring. The second offspring will be something like this, something see here it is changed, so it will be y plus 3 here. What is coming up here will be y plus 3. So y plus 3 minus x, it will be something like this, the second operator, I mean offspring. So this is how the crossover operators are employed in the case of genetic programming. Now, in the case of mutation, you know that only a slight change is done, a random change is done. This is the most common mutation that is being employed in the case of simple genetic algorithm as well as simple genetic programming. So what it does is replace a randomly chosen subtree by randomly generated tree. So this is the randomly selected, randomly chosen subtree. So this particular subtree, the y divided by 5 plus 1. So this is the subtree that is being replaced. So that is replaced with only a y. So that is a randomly generated tree. So y can be a randomly generated tree, or it can be any other trees, no problem, y plus 3 or y minus 3 or y squared, whatever it is. So that can be, that is a randomly generated tree. And this is how the mutation operation is done in the case of genetic programming. And another type of mutation operator, that is another example of mutation operation. So here actually this involves b, another b. So this is b squared, b into b is b squared, b into b. So it is b cube. So this way it is b cube. This is b cube minus square root of a. So that is it. So it is replaced with here it is b cube minus ab, sorry, a plus b. So this is a plus b. So this square root of a is replaced with a plus b. So that is the way the mutation operator is being employed in the case of genetic programming. So then the steps involved in the genetic programming, as in the normal genetic algorithm itself, the steps involved in genetic programming is the same. Create an initial population. So in this case, the initial population should be initial population of programs. Then execute each program in the population and ascertain its fitness. So that is the difficult part. So each program is to be executed for solving the problem at hand. Then its fitness has to be found out. The fitness, what should be the fitness, that is the difficulty. Whether it should be the solution quality, or whether it should be the time taken for solving a particular solving the problem at hand, or is it the memory requirement or the the computational requirement for employing or for running that particular program. So that is actually there are multiple ways how we can ascertain the fitness. Then the select the programs with the highest probability of fitness to participate in genetic operations. So then we go for the selection operation depending on the fitness. So the fitness has to be found out. Then create new programs by applying genetic operations, which are the different genetic operations are this one, the reproduction, crossover, and mutation. After some termination criteria is satisfied, the single best program in population produced is the solution. So this is the same as the genetic algorithm. So then why the genetic programming? Why we should go for genetic programming? That is, there are different advantages based because of this genetic programming. It saves time by freeing the human from being from having a design complex algorithms. The human beings does not have to design complex algorithms or check different algorithms. Not only designing the algorithms, but creating ones that give optimal solutions. So if the computer can create the algorithms on its own, then it will be better. So that is how genetic programming works. Then it combines genetic algorithms with the basic thrust of AI, which was to get computers to do things automatically. The AI means AI is artificial intelligence. You know what it means. The computers has to do the things on its own. So if the computer does the programming also on its own, that is better. So that is how the genetic programming is important to AI. If the genetic programming can be implemented efficiently, it will be a very good boost to the AI program that is being run. So that is it generates some multiple solution. I mean multiple programs also. It generates a population of programs. Then it is difficult, unnatural, and overly restrictive to attempt to represent hierarchies of dynamically varying size and shape with fixed length character strings. So that's it. In most of the cases, the difficulty in representing the program codes is we cannot represent them as a fixed length character strings. Instead, we have to go for some sort of tree-like structure. So when we are going for a tree-like structure, it has to implement the genetic programming concepts. The genetic algorithm concepts are employed into, or they are tailor-made to do the genetic programming operations also. So for many problems in machine learning and artificial intelligence, the most natural representation of a solution is a computer program. That's it. So you have to find out a number of computer programs for efficient working of machine learning and artificial intelligence. So the solutions to this machine learning problems or machine learning problems as well as the artificial intelligence problems is a computer program, and that computer program should be represented in a natural way. It cannot be represented as a character string. So that's the importance of genetic programming. And the difference between genetic algorithm and genetic programming lies in different ways. One of the way, the flow chart. So in the case of genetic algorithm, the flow chart is only like this, without any branches. It doesn't have branches. There is a population. We have a population. Then we select individuals, perform crossover with some probability, perform mutation with some probability, add offspring to the intermediate pool. Then the next generation is coming up. Then the next generation is created. So this repeats. This goes on repeating. But in the case of genetic programming, the difference is that what you say, the individual is selected at randomly or with using some probabilistically. Then whatever goes through the crossover, some is going through the crossover and some others are going to the permutation. Not the one that is going through the crossover is not again going through the mutation operations. So that is the difference. Then one is added to both the offsprings are added to the same what you say intermediate pool, and then the next generation is found out. That is one difference. And the other difference is in the representation of the chromosomes or the individuals. In the case of our normal genetic algorithm, it is simple representation. That is, mostly it is a character string representation. If the character string can be binary string or a permutation string, etc., etc. But in the case of genetic programming, it is program codes. So that is the tree representation is syntax tree representation is used in the case of genetic programming. So that is the main difference also. And that's all for today. That is that's all for about genetic programming.